Yeah, let's get started. So in this lecture, we are going to continue to talk about transactions. Right? So in the first 5 or 10 minutes, let's just quickly go through what we know about transactions, get on the same page about, essentially what we know so far, right? Then we are going to continue to talk about isolation. So we start our exploration of transaction starting from this example, right? You're running a bank, you're maintaining a whole bunch of databases, right, containing how much money people have in your bank. So if you have these two different transactions, right, withdrawing money from the same bank account, but if you mix them in different ways, right, we saw, that could cause problems, right? At some point, if you are not being careful in how these two different transactions have been mixed together, right, you are going to have those undesirable behaviors, right? Someone going to withdraw more money than whatever she may have. So what is missing here is actually the notion of grouping those instructions together to tell the database, okay, so these are not independent instructions or statements. So those actually belong to a single group. When you run those group of statements, I want you to enforce 4 of these properties. And we talk about atomicity, we talk about consistency, isolation, and durability. Once we introduce this notion of a group of statements, which we call transaction, we can actually formally define the contract between the system and the user. Once you give me a transaction, we want to understand, first one, what each of these properties really mean, and second, how can we build a system to enforce each of those properties in an efficient way. So let's just quickly go through these 4 different properties. What is atomicity? Right? Atomicity means that, right? So a transaction is either executed in the entirety or not at all. You never see kind of an intermediate update stage being committed into your database system. Essentially, whenever your system running, someone pull the plug, pull the plug in the middle, the system crashed, right? And then we'll reboot the system, we'll recover from that failure. You are only expecting to see 2 states. Either the transaction is done, or none of the changes from the transaction is in your database once you recover from your failure. You will not see anything in the middle. And we have consistency, right? Which essentially means that if I give you a database, in the beginning, it's consistent in the sense that all the integrity constraints being respected. Once you run all those transactions, at the end of the day, I will also have a database system that is consistent, where all the integrity constraints are respected. And we have isolation, right? If you have multiple of those transactions running at the same time, we want to have the behavior from the system that is as if those transactions are being executed one by one. And we have durability, right? Once I tell you the transaction is being committed, then it's committed. I will never roll back like a committed transaction. No matter how many times your system going to fail. So starting last week, we talked about these 4 different properties. And we start to think about how can we formally define them, and how can we design a system to enforce them. So just formally define it, right? So we think about database as a collection of objects with name, okay? And then each transaction is a sequence of read and write operations. We can say, we read this object A, right, from database to some in-memory object. You can also write it back, right? So here, our assumption is whenever we are writing it back, the changes are actually reflected in the database immediately. That is, whenever there is some other transactions read the same object, it's going to see your latest write. And the new transactions start with begin and can end in 2 different ways. Either you commit, which essentially means that all the changes from this transaction are going to be reflected inside your database, or you can abort, right? So essentially, all the changes are being rolled back. So it could be issued by the user, right? You can say, I don't want to do this transaction anymore. I abort the transaction, fine. It could also be issued by the database system, right? So last Friday, we looked at one example where the database is going to issue the abort statement for your transaction sometimes. When you have deadlocks, right, you need to kill some of the transactions. The way for the system to do it is to actually pick some transaction to abort. So the abort could be issued either by the user or by the system. So just look at one very simple example, right? We have like this example we looked at last time, right? So so assuming you have the entirety constraint A equals to B, right? In the beginning, right, I may have a database system where A equals to B is respected. If you look at each of these transactions, right, they are going to respect the entirety constraint in the end. So a schedule, we talk about schedule. A schedule is a specific way for you to mix these instructions together. You could have serial schedule, where you actually run the instruction from one transaction first, then you run the other transaction, right? So this will bring the database state from, for example, 10 and 10 to another consistent state. In this case, 220 and 220. But not all the schedules are serial, because you are able to actually mix those things.
In a match like this, they work hard and burn it to draw it back into a 1-1.
Okay. Okay, so not all the schedules are serial, right? Because as you can look at here, you are able to mix these instructions actually together, right? You can run the first half of T1 first, then you run the first half of T2. It's also going to bring the database state from somewhere to another place. Here from 10 and 10 happens to reach the same state. If that happens, we say this schedule is serializable because the result is equivalent as some serial schedule. But of course, if you look at this, there are different ways for you to define serializability. You could say, in the current database instance, I run this schedule, and then I get the same state. Or you can say, I don't care whatever database system you gave me. I can prove the schedule is always going to be the same as some serial schedule. The second one is more restrictive, right? Because if you take the first view, you could just be lucky, right? In this database instance, I'm kind of lucky. The computation I'm doing have some property such that on this specific database instance, I get the same thing. That's not what we want, because it's very, very hard to check. We also introduce a stronger notion of serializability called conflict serializability. The high-level idea is by defining a whole bunch of pairs of conflicts between those operations. And then essentially, what do we mean by conflict? Conflict means that I cannot swipe the order of those two operations. Once I swipe them, they are not equivalent anymore, which means that I'm able to find some database instance such that they are going to give me different result. I'm defining all those pairs of conflicts between operators, and we say if two schedules are conflict serializable, if and only if we can transform one schedule into the other one by swiping adjacent non-conflicting pair of operations. So this is just one example, right? We take a simple disk schedule. You say, OK, now we have read A and read B. There's no conflict, right? I can swipe the order. I can read B first, or I can read A first, read B. Doesn't really matter. No matter what database instance you give me, I'm always going to give you the same thing. So I can swipe them, right, to generate a new schedule, and then can look at the new schedule to say, yeah, the write A and the write B, yeah, I can swipe the order. There's no problem. I generate a new one. You say read A, read B. Yeah, I can swipe them. I keep doing this until I reach a serial schedule. If I'm able to do that on some schedule, I say that schedule is conflict serializable. So of course, there's an easier way for you to check them. You can actually take all those pairs of operations and construct a graph, a dependency graph, look like this. Essentially, if you have an edge from T1 to T2 in this graph, it means that there exists some operator in T1 and some operator in T2, that the operator in T1 happens before the operator in T2 that are conflicting with each other. Whenever there's a loop in this dependency graph, right, so you have a schedule that's not conflict serializable. Okay? That's an easy way for you to check that. And then we talk about how to enforce isolation, right? How can we generate a schedule that actually conflict serializable? And last time we talked about a very specific view of that. That is by taking a very pessimistic view, in the sense that conflict will happen all the time. we have to do something. If we do nothing, you are going to have a case very often that database is going to be inconsistent. So we need to prevent the bad thing from happening every single time someone tries to do something. And the way to do it is by holding locks. Before I can do anything, I need to acquire a lock. So we are going to finish up a little bit about that today. And then we are going to talk about another way of looking at the problem is by taking a very optimistic view. The optimistic view is, okay, I know in the worst case, yeah, it can be very bad, okay? But that probably won't happen too often. So it's going to be very expensive if I try to prevent you to do things just to, I'm so afraid something bad will happen. What I'm going to do is I ask everyone to do whatever they are trying to do. And then I'm going to check whether something bad really happened. If that really happened, I'm going to roll back your progress. Otherwise, I will ask everyone to proceed. So today, we are going to look at these two different views. Now, let's look at the pessimistic view, right? So we talked about that last time. There's something that we need to finish up. So the way to do that is by holding locks. So the one assumption is we don't know what the transaction is going to do in the future, okay? So when we talk about schedule, you always think, yeah, so that's a whole transaction. You don't know, okay? At the current time point, I know what has been issued into the system. I don't know what you are going to do in the future. That's one assumption. The high-level idea is before the system accesses the data object, either read or write, is try to hold a lock, and then such that other transaction cannot do things on that object at the same time. And system only release locks when it's safe to do so. So there are two fundamental questions. First one is when to acquire lock, and second one is actually when to release lock. So this is actually an example about how the lock manager works, right? So here, T1 acquire a lock, right? Lock manager say, yeah, no one is having this lock on A. I give that to T1. And then when T2 try to acquire the same lock manager going to ask it to wait until T1 unlock the same object. It's something like this. And we talk about two different ways you can acquire and release lock. The first one is called two-phase locking, right? In this case, in the very beginning, you can acquire locks, and then you can only release locks in the second phase, okay? And then the second way is called strict two-phase locking. It's the same. You have one phase where you acquire locks, but you hold all the locks until the very, very end of the transaction. And we talk about the pros and cons for each of this. And today, we are going to talk more about locking. We are going to talk about the granularity of locks, and also how to enforce different isolations, like different isolation levels by using locks. So let's look at why do we need granularity of locks. Because if you look at database system, right, we think about them as a collection of objects. But those objects have relationships. There's table. A table contains a whole bunch of tuples, and tuple contains a whole bunch of values or cells. There could be billions of those tuples. So let's look at these two transactions. In T2, right, I'm trying to run two analytical queries. I try to take the sum over all the tuples. I keep running this, two queries. And then in T1, I'm trying to insert some tuple into this relation. What should I lock? One thing that's actually interesting, if you think about, I only holding locks on tuples, it will cause problem. Because when T2 run the first SQL queries, I'm only holding locks on what is there. T1 insert new tuples is going to be fun because no one's holding those locks on those new tuples, right? And then T2 run it again. So if you're only holding these logs on the tuple level, this could cause problem. So we have to, in this case, holding logs at table level. I need to log the whole table from T2. Now let's look at the other example. What if we only have table level log? Well, that's going to the concurrency is going to be pretty low because it means that at every single time, only one transaction can look at one table at a time. Another thing about granularity of logs is to consider this query, right? I'm looking at all the tuples inside my database, and for each one of them, I update it. What log should I hold, right? In this case, if you hold those like tuple level logs, it's going to be super expensive because if I have 1 billion tuples inside a relation, I'm holding 1 billion logs. That's super expensive, right? So either for the correctness property or for performance, for speed, I kind of need to consider that my database contains a hierarchy over objects. And we need to try to understand how can we do better. So essentially, the database is a hierarchical structure. On the top, there's database. Okay? There's some operation you need to hold log on database, okay? Like create a database, for example, right? So, and you have a whole bunch of tables, right? Each table contains a whole bunch of tuples. Each tuple contains a whole bunch of attributes. So we have this very natural hierarchical structure in the database system. How can we lock it? Now let's consider a very naive strategy which will be wrong, okay? What if you do this? For each object is lockable, right? I can acquire a whole bunch of logs. I can acquire a log on table 1, I can acquire a log on tuple 1, whatever. And then different transactions just lock objects as if they were locking tuples in two-phase locking or strict two-phase locking. If some transaction to say, okay, I want to lock table 1, I just give the lock on table 1, then no other transaction can access table 1. Some say, yeah, I want to lock tuple 1, yeah, give the lock to tuple 1. What's the problem of this? The problem of this is we're looking at this example. I have two transactions. The first T2 want to lock tuple 1, and T1 want to lock table 1. Okay, and their lock, the T1's lock is yellow and T2 lock is black to make sure like we know what it looks like. So what should I do? T2 asked for the lock on tuple 1, yeah, I gave that to T2, it's fine. Right? I'm holding lock on this object. Should I give T1 the lock when T1 want to lock table 1, which contains tuple 1? So if you do nothing, if you just treat these objects as independent objects, you will give lock of table 1 to T1. Why? Because they are different objects, right? So, I mean, it's clear that this will cause a problem because T1 cannot do whatever it wants on table 1 because T2 is holding the lock on tuple 1, right? So we need to do something way better than this. So the problem is that this one will actually not enforce reliability at all, right? Another naive strategy looks like this. What if, before granting T1 the log on the whole table, I try to probe all the tuples in this table? I try to ask the database, okay, do you have anything that is holding log on attribute 1? Do you have anything holding log here, holding log here, holding log here? I ask the log miner to give me all the status of logs for all the objects contained in that table. And database will say, okay, someone is holding this, so you cannot do that. So what's the problem of this strategy? And this one, first one is correct, right? So we have something that's actually not that wrong, right? You are going to have something consistent. But the problem is going to be super, super slow, right? Because when you have billions of those tuples, you need to probe it maybe billions of times.
Would we get a problem if we like probe it and then while we are probing it, one that we already have checked gets locked?
Oh yeah, exactly, right? So like exactly that problem, right? So like during the probing process, because you are probing like 1 billion things, right? Probing 1 billion is very slow. Like 1 billion operations, like one CPU cycle, something. No. So like 1 second, something like that, right? So during that time, it's entirely possible someone else change the status, right? If you really want to do this, you need to hold a lock for locks. You need to say, oh, I'm checking things. No one release locks. No one acquire locks, right? So this is going to be really, really slow. So we have to do something in the system side to make sure it's both correct, take the advantage of all the hierarchical structure, and second, be reasonably fast. So very beautiful thing people were doing back in the 70s or 80s is people start to introduce a new type of locks. So we have the shared lock, we have the exclusive lock. But then people start to introduce 3 different new type of locks. The first type of lock is called intention shared, which essentially means that if I have the intention shared lock on some node, I'm actually telling you some of the lower level node are in the shared mode. Okay? That's the semantic of this lock. Another type of new locks is called the intention exclusive. If I'm holding this as some node, it means that some lower level node are in the exclusive state. And we have the shared and the intention exclusive, meaning that the root, like that node, is locked in shared, and there are some other lower level node are in exclusive. Once we have these 3 different type of locks, when the system wants to lock something, we go all the way from the root to the bottom. If the system wants to say, okay, lock tuple 1 in shared state, like I have a shared lock on tuple 1, we'll start from the root and say, I will acquire intention shared lock on the whole database, meaning that some of the tuples will be in shared state. So we have intention shared on database, we have intention shared on table 1, and then we acquire the shared lock on tuple 1. You go all the way from the root to the leaf node. Once you have these 3 different new type of locks, the compatibility matrix becomes a little bit more complex, but it's kind of easy to reason. So let's look at it. So let's look at this. So assuming there's some transaction holding, for example, exclusive lock on table 1, and then I have another transaction coming in. I say, okay, I want to intention share lock on this table 1 too. Can I give this lock to that transaction? And from the compatibility matrix, it's no, I cannot. But why? Someone is holding exclusive lock on table 1. It means that the expectation of that transaction is I can do whatever I want on table 1. If you try to acquire intention share lock on table 1, your intention is I want to update some tuples in this. I want to read some tuples in this table. Clearly, I cannot give that to you because there's another transaction try to update the whole thing. So essentially, these 2 locks are not compatible, so the intention share lock need to wait. So what if, for this case, there's some transaction holding intention exclusive, and some other transactions say, okay, I want share lock on this. Who think we should give the lock to that transaction? Who think we shouldn't? Who don't know? Who don't know? So in this case, right, so someone holding intention exclusive means what? Means that that transaction will update some tuple in this table. It's holding exclusive lock on some of the tuple here. Not on the table part. It's try to have some tuple holding exclusive lock. If someone else have a share lock on table 1, clearly no, right? Because having share lock on table 1 is equivalent of having share lock on all the tuples, right? There must exist one tuple that will cause problem because there's some other transaction try to update some of the tuples. So in this case, no. Okay? In this case, the share lock need to wait. So now let's just try to simulate like the process, okay? So assume you have T1, you have T2. T1 say, I want to share lock on tuple 1. T2 say, I want to have exclusive lock on tuple 2. So here's how the lock manager is going to do this. It's going to go from the root to say, okay, you want to share lock on tuple 1. I need intention share lock on all the upper layer. I will try to acquire intention shared on database. In this case, there's no lock in the system. You're going to get it. Once I get it, you'll have intention share lock on table 1. And then you try to acquire share lock. Now, transaction 2 going to log tuple 2. The same thing. It's going to ask database, okay, can I get intention exclusive lock on the database? This one's fun, right? Both are intention, right? If you look at compatible matrix, right? So it's going to, yeah, fun. You have that. And then it's going to go one level down to say, okay, so I also need intention exclusive on table 1 because I want to update some of the tuples. Database will say, okay, fine, yeah, it's fine. And then try to have the lock on tuple 2, the exclusive lock. If you look at this, right, so this is the state of locks in the system. There are multiple, essentially like table 1, if you look at the table 1, like there are different transactions holding 2 locks, intention share, intention exclusive. What does that even mean? It means that in the current system, there are some transactions try to update some tuples in table 1, and there are some transactions try to read some tuple in table 1. That is what that means, that 2 locks. Okay? So in this case, we are lucky because these 2 transactions are dealing with 2 different tuples. So they can hold they can hold locks on those 2 different objects without any problem. Okay? So this was going to happen. What about this case? Table 1 to say, yeah, I want to have a share lock on table 1. The transaction says that. Then I have intention share lock on database. Then I share lock table 1. Transaction 2, okay, I want to have a share lock on tuple 2. It's the same process. It's going to say, yeah, can I get a intention share lock on database? In this case, yes. Can I get intention shared on table 1? Okay. And then you get the shared on tuple 2. Okay. So, any questions about this granularity of locking? No? Okay. So one way to learn about this is when you go back home, right? So this is something you really need to just go back home and stare at the matrix for 1 hour. I did the same thing this morning. Yeah, trust me. So look at that matrix, okay? For every single cell, you try to think about why these 2 locks are compatible or why they are not compatible. Okay? I hope I have a better way to teach you how to deal with this. But essentially, what I do this morning is I go through every single cell. I say, okay, can these 2 locks happen on the same node, right? So the way to think about that is try to think about what does it even mean for someone to hold in a specific type of lock on a certain node. And once you understand that, the whole thing will become pretty natural. It's not trivial, but very natural. Okay?
In what cases do we need the 6 lock?
Oh yeah. So sometimes, for example, you have a query look like this: update relation set a equals to 5, where b equals to 10. Okay? What do you need to do? You need to read all the tuples and update some of them. That's shared intention exclusive. Right? I need to read the whole thing, but I don't update everything. So I do not need an exclusive lock on that level. I update some tuple. That's where the SX comes in, right?
Couldn't we then use like 2 different blocks? So first for reading everything, requiring a shared lock, and then doing a intention exclusive?
I can imagine a way for you to implement that. But if you say, I do not want shared intention exclusive, so what I'm going to do is I will say, for this transaction, I acquire just two different set of locks. I acquire shared, then I acquire intention exclusive. Then you need to distinguish whether it is the same transaction asking for the lock, right? Because if there are different transactions, one asks for shared, another asks for intention exclusive, then no, right? So that will make the lock manager very complicated. So that depends on which transaction is asking, which we do not want, right? That's why we have this shared intention exclusive. Make sense? Okay. Any other questions? Other questions? No? Okay. Oh, yeah.
What lock is on parents of 6? Is it EX or EX? If the table is in 6, then what state is database, and what lock is on database?
That's a good question. Okay, so assuming there's some node is in SX. I don't know, actually. What I would say is you need to hold IS and IX on the root, right? Tell the database to say, there's something under you I want to share. That's the intention share. There's something under you I want to update. That's intention exclusive. I would say the naive implementation is you hold that two intention locks. That should be fun. I don't know what PostgreSQL do. Oh, no, PostgreSQL is a different animal. So I don't know what MySQL is doing. About this. But yes, you hold that two locks. Yeah, that one will be correct. I'm not sure whether it's the optimal solution for that. Make sense? Okay. Any other question about this? But go back home, think about this compatibility matrix. It's very natural, but it takes a couple hours to understand this. Okay. Every year when I teach this lecture, I will get up 1 hour early and just look at this. Okay. And somehow I understand this. Okay. Make sense? Okay. So this is about granularity of locks. And then another thing that's interesting is about isolation levels. Because last week, we talked about different levels of isolation. Right? You have serializability, and you have a whole bunch of other levels in the middle. There's a repeatable read, there's a read and committed, read committed, something like that. So for each of these levels, you are actually allowing different type of concurrency anomalies in the system. So how can we enforce different isolation level? We know how to do serializability now, right? By having a strict two-phase locking. But how can we do the things in the middle? So it turns out there's a very beautiful way to enforce that if you know the notion of locks. So we can actually twist the protocol of strict two-phase locking to implement different isolation levels in SQL. You want serializability? Okay. You need to do strict two-phase locking and something called index lock. Index lock is essentially locking the whole table. Okay? So I need to stop some other transaction inserting stuff while I'm doing the things. So I need to hold the table lock, sometimes called predicate lock, sometimes called index lock, right? So, but point is, you need to strict two-phase locking. You need to have the notion of locking the table. Then you have serializability. If you want to do repeatable read, all you need to do is to have this strict two-phase locking at tuple level. Okay? Having strict two-phase locking at tuple level give you repeatable read. Okay, that's very important. It doesn't give you full serializability because you need to lock the table to prevent all those phantom tuple to be inserted. Okay? So serializability in SQL is strict two-phase locking plus index lock the table. Repeatable read, essentially strict two-phase locking over tuples. What's getting more interesting is how to implement read committed. Right? I want to make sure in this isolation level, everything I'm reading coming from a committed transaction. In this case, what I'm going to do is that to have the shared lock released immediately. I do not need to keep my shared lock if I'm in the isolation level of read committed. Because all I'm trying to protect is no one can read from my updated tuple until I commit. Make sense? If you do the read committed level, you can actually release the share lock immediately after you read something. If you do read uncommitted, you do not need to have share lock. You can have a system without share locks. Right? When I'm reading something, I just read it. Okay? So that gives you the isolation level read uncommitted. Make sense? So essentially, you can actually do this. Right? So one thing that's beautiful is all the things we talk about today and actually last week actually come from one paper. Yeah, so that's how good this paper is. Okay? So this is a really fundamental paper from Jim Gray, who actually win the Turing Award because of all of this isolation and concurrency control type of thing. Right? So all we talk about in these 3 different lectures coming from mostly, I mean, not come from, but mostly you can find them in this single paper about granularity of logs, about different isolation levels, right? Different intention log, all the type of things. Okay? If you're curious about this, read this paper. But otherwise, just read the textbook. It's good enough. Okay? Now let's look at some examples. Okay? So let's try to see, look at different examples to make sure you see in practice how the whole thing actually works. So here we are going to do MySQL. We are not going to do PostgreSQL because, as we will see in the second half of the lecture, PostgreSQL is doing something else. Okay? So let's try to do MySQL. Let's look at one example. So I have these 2 MySQL database. Let's make sure we can. Now I have 2 things side by side because I want to introduce essentially 2 different SQL queries concurrently. Okay? So I will try to cite my serializability isolation level. I will first set this session, the isolation level, to be serializable. And then I will do the same thing for the other session. Okay? Now I have 2 sessions that the isolation level is serializable. And then in transaction 1, we have a transaction. Transaction 2, we have another transaction. Okay? And transaction 1 will do something like interesting. I will update relation R, b equals to b plus 1, where a equals to 0, something like this. Okay? It runs. Okay? There's no problem. And then some other transaction come in to say, okay, I want to update R, set b equals to db plus 1, where a equals to 1. What would happen for this thing? If I hit the button, what will happen? And let me think about it. But yeah, who think it will? Okay. So who thinks this one will wait? Who thinks this one will get stuck? Who thinks this one will just run? No. Okay. So it will wait. Why? So let's try to reason about this case, right? So I have a single relation R. In T1, what have I done? T1 essentially says that, okay, I want to update this relation R. For every single tuple where a is to 0, just one predicate, I update it. What type of logs do I need from this one? Well, I need to read everything. I need to have a share log on the table, right? And then I need to update something, right? I need to have intention exclusive lock at the table level, right? And then once you run it, it's going to have that lock. And then T2 comes in to say, okay, I want to do something similar. I want to go into like screenshot scan this table, right? Find all the tuples with where a equals to 1 and update the corresponding one. Once you hit the button for that, okay, now it's timeout, right? So because waiting for the log for too long. Okay. Once you hit the button here, what's going to happen is the transaction is going to say, okay, I need the share intensive, intention exclusive log on that table. because it's the same type of query, right? And to read everything, to update something. And then the system will say, okay, no, someone else is holding shared intention exclusive on this table. You cannot hold it, so you have to wait. Okay, that's actually what happens. Make sense? Any question about this? Yeah, about this example. It's going to get way more confusing than this. Trust me. Okay.
So the left session will only drop the logs it holds right now once you end the transaction.
For serializability, when the isolation level is serializable, yes. Yeah. So one thing I can see is I can, for example, I can either commit or I can roll back. Let's roll back. Okay. First time, because I don't want to change my data, I roll back. And then if you run the same thing, it will be fun. Because once you roll back transaction 1, it's going to release the lock. And then there's no one holding that lock on that table anymore. And the T2 can come in, do whatever it wants. Okay? Okay, now let's roll back both transactions. Now let's look at another example. I have, where's my cursor? Oh, here. So I have this 2 transactions coming in. And my T1 will do this. I just read everything, report number. I select sum from R, okay? As you can see, it runs. And then here, someone is doing some, T2 is doing insert into this relation, values, for example, 3 and 3, something like this. What will happen? What will happen? We have 2 minutes. Yeah. What will happen? Who thinks this one gets stuck? Who thinks this one will not get stuck? Okay. It will get stuck, right? Why? Because my isolation level is serializable, which means that I have table lock, right? When the first transaction tries to read all the tuples, what it's actually trying to do is to say, I have either share log or intention share log on this table. And then when I insert tuple into R, what do I need? I need an exclusive log on this R. I need to lock this table. No one can change this table because I'm trying to insert tuple into it. Okay? So that need to wait. If you commit this transaction, that one will also proceed. Okay? Some of you guys didn't see that magic moment. Okay? So once this one commit, this one immediately proceed. That's concurrency. That's why holding logs can actually make system faster. Because the moment I'm able to make progress, I make progress. That's why even with a single processor, single core, single thread, concurrency can actually sometimes help you. Okay, so now let's look at another example. Where's my cursor? So I have 2 relations. I have R and S. For this transaction, what I'm going to do is update relation S, set A equals A plus 1. Okay, it's fine. For this one, I'm going to update another relation R. Okay, it's also fine. And then what's going to happen is on the T1, I'm also going to update R. And on this one, I'm going to update S. What would happen? Okay, the first one already updated S, that's relation. The second one update R. And then this one I want to update R, this one I want to update S. So let's take a break. When we get back, we'll hit the button together. Okay? Yeah. Okay, so let's get started. Can people on Zoom hear me? Perfect. Okay, so let's go back to these 2 transactions. Okay, 2 transactions, wait 15 minutes, wonder what we are going to do with them. Okay, 2 transactions, T1 and T2. So what do we have so far? I mean, yeah, T1 essentially update S, and T2 update R, and T1 want to update R, and T2 want to update S. Okay? So we didn't hit the button. What if I run this query in T1? What will happen? Who think going to get stuck? Who think it will proceed? No? Yeah, so this one will get stuck, right? Because, yeah, T2 is holding lock on R, and I need to wait for it. And what if I also hit the button for this query? Who think going to get stuck? Okay. Who think it will not get stuck? Who think it will throw an error? So on the theory side, what are we expecting? Well, I mean, there's going to be a deadlock because they are waiting for each other. It's going to trigger something really magical we talked about last week about deadlock detection, right? So here the system is going to say, okay, here's a deadlock. And then what it will do? It will try to kill some of the transaction. So once I hit the button, what I'm expecting is it trigger deadlock detection and try to pick one transaction to actually kill. So let's see whether that's true or not. Okay? Okay, so look at this two screen. Okay? Yes, okay. Okay. So this one's going to get stuck. On the other hand, no. Sorry, waited way too long. Yeah, so this one gave up already. No, cannot be do this. No, yeah. No, I cannot. Yeah, so essentially what happens is like I talk too much in the middle. So like transaction one just gave up. Yeah. So no, we cannot do that. Let's restart. Everyone begin. This one hold lock on S. This one hold lock on R. This one say let's update R, and then this one will update S. Okay. If you look at what happened, you can observe two things. Magically, this one proceed. But why? It's because if you look at this one, once you trigger the second query, the system says, okay, there's a deadlock. What I'm going to do, I will kill this transaction. Okay? Essentially, it tries to actually restart this transaction. Or like, in this case, just abort the transaction. Once you abort this transaction, you are going to release all the logs that this transaction hold, and the second one proceed. Make sense? This is actually what happens in practice, at least in MySQL, in the standard configuration, that you have the deadlock, system going to detect it, and going to try to resolve that for you. Make sense? Okay. As you can see, there's another demo. Yeah. Okay. So okay, all those queries are here, right? When you go back home, you cannot reproduce this in PostgreSQL, and you are going to know why relatively soon. But when you go back home, do MySQL, and the SQL query are here. Okay? So the question, yeah.
Will it always kill the first query?
Yeah, so that's a very good question. That depends on so many things. So that also depends on how much progress the system think you are making on the second query, right? So in this case, they are pretty symmetric. They are doing the same thing, and one is a little bit older, right? So this one have a new query. We will not be surprised if you kill the first one. But for example, if I have a case where the first one have been running like 100 SQL queries, then the second query is fresh. The second transaction is very fresh. The first thing trigger deadlock. Probably, I can imagine some database will kill T2. Yeah, because it's such a waste to kill T1, right? So at some point, there's a very dedicated trade-off, and the cost model here is not always going to kill the old one. Yeah, make sense? Yeah. Any other questions? Questions? No. Go back home, install MySQL, and play with it. Okay. Oh yeah. Hey, where's my? Okay. Now we know how to enforce isolation by locks. Now let's go beyond locks, because there are different ways you can enforce isolation by actually taking a very different view about how to prevent bad things from happening. So far our assumption is, the reason we always hold locks is if you do nothing, bad things will happen. That's our assumption. But what if you have a very big database, people are doing all those concurrent queries? It's very rare you have non-serializable behavior, but it could happen, so you need to do something about it. But most of the case, it's going to be fun. If you are living in that world, if that is your workload, holding logs before every single read and write operation could be very, very expensive, because most of the cases, I'm holding the log for nothing. Even if I do not hold log, nothing bad will happen most of the case. So that actually inspired a whole bunch of another line of work in concurrency control, isolation enforcement, is what people call optimistic concurrency control. Now let's look at a very simple protocol here and try to improve over that. The intuition is very simple. What is our goal? Our goal is to guarantee serializability, right? So if non-serializable behavior is very rare, what I could do is for all the transactions in my system, I define an order. So now this is the serializable order I want to enforce. I have T1, T2, T3, right? I want to enforce this order. And I assume that is my serializable order. Whenever some transaction try to read from the future, like T2 try to read from T3, or T2 try to overwrite T3. I know that's not possible under this order. And there could be another order that happens, I don't care, okay? I have predefined order, I try to enforce it. Whenever there's some transaction try to read and write from the future, I roll it back. And during the execution, I do nothing else. That's all I do. That could give you some notion of isolation. The high-level idea is each transaction is assigned a timestamp. Okay? So you have transaction TI, you have the transaction timestamp, TSTI, and you have other things. If your transaction TI has a timestamp that's earlier than transaction TJ, then the database will say, okay, whatever TJ or TI can do, it need to respect the serial order that TI is before TJ. And then I only allow those operations that I know is going to give me something equivalent to the serial schedule that TI appears before TJ. How to assign timestamp? There are so many different ways. You can do system lock, you can have a logical counter. As long as the timestamp is monotonically increasing, unique for each transaction, I'm happy. And then each database object is also associated with a timestamp. The read time of X is the largest timestamp of a transaction that has read X to make sure I do not read into the future. Okay? You have write time X, which is the largest timestamp of a transaction that has written X. Once I have this, whenever I'm trying to read or write an object, I have a way to test whether I'm reading from the future or not. If I'm reading from the future, I need to kill this transaction. Otherwise, I let everyone proceed. If the non-serializable behavior is really, really rare, highly likely the number of rollbacks I'm going to have in the system is very small. Because rollback only happens when you have this non-serializable behavior. So essentially, each transaction read and write objects without locks, okay? Without holding any locks. That's read and write. And each object is tagged with the timestamp of the last transaction that has a read and write, the largest timestamp. If TI try to access the objects from the future, you abort and restart TI. So imagine you have transaction TI, want to read an object X with a write time of x is larger than the than timestamp of ti. This means that the x is being written at this moment by a transaction happens after ti. So if that is the case, I cannot read it. Ti cannot read that, because the moment ti read it, you break your serial order that you are assuming. So in this case, that cannot happen. I will abort ti, restart. Okay? And then imagine ti want to read x with a write time that is smaller than the timestamp of ti. What does this mean? This means that I'm trying to read an object that are being updated by a transaction happens earlier than me. I'm ti, okay? Happen earlier than me. That's fine. Right? In the serial order, there's nothing stops me from doing that. So I will just read it, and then I will update the read time of x to say, okay, now ti is the latest transaction, is the largest timestamp that read this object. I need to update it. Once every single time read or write, I need to update that value. So imagine you have ti want to write x with a write time that's larger than your timestamp. Do we allow it? Who think we should allow it? Who think we should not allow it? Who are still thinking? No. Yeah, no, right? Because your timestamp of ti is smaller than the write time of x, meaning that on the object x, there's some other transaction happen after me already write it. I cannot overwrite a future transaction in the serial order, right? So I'm not allowing that. What do I do? Abort ti, restart. And else, I mean, if it's not the case, right? So on the other hand, you have your write time of x is smaller than the timestamp of ti. You allow ti to write, and you need to update the write time of x correspondingly. Now look at this one. Assuming ti want to write x with a read time of x is larger than the timestamp of ti. Do you allow it? I'm trying to write an object, and no, future transaction already read it before I write the value. No, right? That won't happen in the predefined serial order. That will never happen. I will not allow it. I will ask everyone to wait. And if the timestamp is in the other direction, I will allow ti to write and update the write time. It's as simple as this. The way to think about it is for every single transaction, you have a timestamp. And that gives you a predefined serial order that you are going to enforce. It might not be the optimal one, but that is the only one you want to enforce. And then every single time you read or write from something, you try to use these three different values, the timestamp, the read time, and the write time of certain object, to read a value that's really possible under that predefined serial order. If not possible, I just kill this transaction. If it's possible, I proceed. That is what we mean by being optimistic, because what we are actually doing here is assuming most of the case, even if you do nothing, nothing bad will happen. The probability that the rollback something is going to be very low, that's our assumption on the workload by being optimistic. So this one will be very, very efficient compared with holding logs. Now let's look at one concrete example. We have these two transactions, T1 and T2. And T1 have a timestamp 1, T2 have timestamp 2. Essentially, I try to enforce the serial order that T1 happens and then T2 happens. That's what I want to do. Now we have this schedule. And then here, we have these four important numbers. We have two objects, A and B, okay? We have these four important numbers. The read time of A, write time of A, read time of B, write time of B. Let's try to follow the evolution of those states and try to reason about whether each of these read or write operations are possible or not under optimistic concurrency control. The first thing is, okay, everything begin. In the beginning, I have everything 0, okay? all the timestamp is 0 for all the objects, means that no one have ever read and write all of those, any of those. And then T1 try to read something. Do we allow it? Well, there's no reason that we should stop that from reading B, right? So no one have ever read B in the system, right? Why not? So we'll allow T1 to read B. And then I will update the read time of the objects to say, okay, transaction 1 with timestamp 1 already read that object. The read time of B become 1. And then I proceed. When T2 try to read B, do we allow it? In this case, T2 going to see, okay, so I'm transaction 2. My timestamp is 2. I can only read objects in the past, right? Because the serial order is T1 to T2. Before I read B, I need to check the read time and the write time of B. And now I see, okay, the last transaction, the largest transaction, the latest transaction, okay? So with the largest timestamp, read B is 1. It happens in the past, okay? And then I say, yeah, the write time of B equals 0, meaning that no one have written anything on that yet. So it's fine. So I'm going to read it, okay? And then once you read it, you are going to also update the read time of B because now transaction 2 read B. And now you say, okay, transaction 2 want to write B. Yeah, the same thing, right? Going to check the timestamp of B and try to update it, right? In this case, you're going to update the write time of B also to 2, meaning that the last transaction, not last, the transaction with largest timestamp that have ever written to B is 2. And then T1 try to read A. The same thing, right? It's different objects, right? So why not, right? Of course, I'm going to allow that to read it. And then T2 try to read A, try to write A. Of course, I'm going to allow all of those. And every single time I do something, I update the timestamp. T1 commit, T2 commit. So as you can see, if you have this schedule, I do not need to hold logs at all. All I need to do is to check the timestamp, and then they do whatever they're supposed to do. Both can commit. It's serializable. There's no violation at all. So that is why if your assumption that you are able to be optimistic of the workload is correct, optimistic concurrent control could be very, very efficient. There's no logs at all. Okay? Now let's look at another example. Again, in the beginning, we have all those 0, 0, 0, 0, these 4 things. Now T1 read B, of course, why not, right? So I update that. Then my read time of B become 1. My T2 read B, yeah, why not? It's fine. T2 write B, yeah. Now T1 want to write B. Should we allow that? What should we do? T1 want to write B. I try to check the read time and write time of B. Who think we should allow this? Who think we should not allow this? We should not allow this because I'm T1. I'm supposed to happen before T2. I cannot write to a value. I cannot overwrite T2. There's no way in the serial order that I have the chance to overwrite T2. Because T2 should happen after me. In this case, I roll it back, just abort T1, and T2 proceed and commit. Okay? Makes sense, right? So if you do this timestamp thing, right, going to general schedule, that's confident serializable, right? Why? Because you never read and write into the future. If you look at all the pairs of config operations, it's always happen from the earlier transaction to a later transaction. If you construct dependency graph, you will never have loop because the information never flow from the future back into the past. There's no deadlocks because there are no locks, right? So they never wait for each other, okay? So that's why it could be very, very fast. But what's the problem? What's the problem of this? So there are actually multiple problems. The first one is, if you are being optimistic when you shouldn't, this one could be very slow. If you live in a world that this non-serializable behavior happens all the time, and you use the optimistic concurrency control like protocol, it's going to roll back all the time. No one can make any progress, right? So that could be a problem. But another problem is when you have a very long transaction, and then you have a whole bunch of smaller transactions. Here, T1 is super long, a lot of statements, instructions. T2, T3, T4, those small transactions happen after T1. If you think about this case, you are having this unfair disadvantage on T1 because T2, T3, T4 are going to do whatever they want to do. And because T1 is so long, highly likely you are always going to roll back T1 because all the other small transactions are way too aggressive in changing things. So sometimes you have this very long transaction that just starve to death because you can never get anything done. You try to run a whole bunch of those in the middle, roll back, right? You restart in the middle, you roll back. Simply because there's so many things you want to do there. The risk that transaction going to be rolled back, assuming all the conflict happen uniformly, is going to be much higher than those smaller transactions. So that could happen, right? So another problem is cascading abort, right? Here we talk about isolation, it's fun, but whenever some transaction try to abort, that could cause a problem. If you look at this case, right? In the beginning, T1 want to write B, yeah, update it, right? I allow you to do it. T2 read B, can I do it? Yes, yeah, why not? Yeah, so T2 can read B, right? Because T2 happens in the future, yeah, it can read the past, fine. T2 write A, yeah, sure. T2 write A, and T2 commit. I shouldn't stop T2 from committing, right? I don't have the mechanism for that. So T2 commit. And then what if, at this point, T1 abort? In this case, that could cause a problem because T2 read from T1. But now T1 abort. So I should also abort T2, but T2 is already committed. What can I do? I cannot have a durability in this case because I need to roll back a committed transaction. So that will cause problem. There's some way to fix it. Right? If you go to the textbook, there's actually one section just about how to twist this protocol to make sure you do not have this cascading abort behavior. But now let's look at a different protocol. We are interested in this protocol because that is actually what PostgreSQL actually tries to do. It actually tries to do something extremely beautiful called snapshot isolation. It's similar to how GitHub works. The high-level idea is like this. It's also being optimistic. What I do is you have a database. Whenever some transaction start, I fork it to create a sandbox. I just copy this database. And this transaction runs within its own sandbox, do whatever it wants, never wait for each other. When some other transaction come in, yeah, I copy the database, copy in a logical sense, copy the database, have a sandbox. The other transaction run in their own sandbox. When some of them want to commit, I merge the sandbox back to my original state. If the non-serializable behavior is very rare, I should expect the probability that I'm able to merge something back without conflict is very low. So I'm happy. If I cannot merge something back in the provably correct way, then I roll back that transaction. That's a high-level idea. So as you can see from this figure, right, you have original like a database. There are two transactions coming in. What I do is I copy this database into two different databases, run T1 in one, run T2 in the other. I get two databases at the end. I merge it back. I see whether there are conflict or not. If you are using like a GitHub, it's like T1 have a pull request, T2 have a pull request. You try to merge. You try to see whether you are able to merge them or not. So that's a high-level idea. So as you can see, this one is also extremely powerful because none of those transactions need to wait for each other. They operate on their own sandbox. So that's the high-level idea called snapshot isolation. Every single transaction works on its own snapshot. The high-level idea is when you have transaction T start, it receives a timestamp. And then each timestamp corresponding to a version of the database. All the read from T happens on the database version corresponding to timestamp of T. Okay? You just copy it. You keep reading that database. And all the write are reflected in a separate buffer. You update your local snapshot. And then when you commit, you try to check whether there's conflict or not. How can I check the conflict? So assuming you are trying to check commit T1, the thing you are trying to check is assuming you have T1 and T2, kind of when they start, you copy the same database into two things. You think you try to check whether there's another transaction T2 committed before T1. Okay? When in T1, when you try to you see whether there are T2 committed, and you see whether T2 update the same value as T1. Because if that happens, there's no way you can merge the sandbox of T1 back to your database state. Because you need to, because then you are going to overwrite the update from T2, which is supposed to happen after you. Okay? So that's what you are going to check. So this is a high-level idea. So why is it so efficient, right? So in this case, read and write do not block each other at all. If you look at the previous one, right, for the timestamp, for every read and write, I need to check the timestamp. I don't want to do that. Here, they do not wait for each other at all. They just proceed. In the extreme case, really extreme case, if you have a transaction that's read-only, like all the transactions are read-only, okay? They only read stuff. You will never have rollback. And then every single transaction will proceed as if all the other transaction doesn't exist at all. So of course, this has problems, okay? So as we will see later. But now let's look at some example. So of course, in real database, it's not going to copy the database because it's really too big. So what it's actually try to do is actually try to keep different version of each tuple. So for each of this tuple, it actually maintains different version. For example, here you have the value 100 for A. Right? In the beginning, you say, yeah, one version of A with value 100. And you have this begin and end corresponding to a range of timestamp, right? That you say, yeah, for all transactions within this range, they should use this copy. For all the other transactions in that range, I should use this copy. In the beginning, I have one. That is fun. When T1 starts to read, it doesn't really have a choice. Have like only one copy is going to read that, right? So, and then when T2 tries to write, what's going to happen? When T2 tries to write, instead of overwriting the first version of the database, it's going to create a new version of the value. So yeah, T2 wants to write A as was 200. I create another version of A with value 200, and then I update the begin and end value for each version. In this case, I will say, yeah, A0, original thing, should be used by transaction with timestamp between 0 and 2, because that's the old version, right? And then everything after T2 should use the second version. You keep this interval of timestamps for each of this value. And then when T1 want to read A, which value should it read? It should read A0 because it works in its own sandbox. And then try to commit. In this case, yes, it's going to check whether I'm able to commit or not, right? Can I commit? Yeah, in this case, essentially you check whether there are other transactions that commit earlier but updating the same thing. Yeah, no, T2 hadn't committed. And then, so I commit T1, and T2 read A. Which value should T2 read? T2 read the second version of A, right? Because that's my sandbox. And then you commit. So both are fine. You are able to merge them back. Now let's look at this example. Again, when I begin, I have A equals 100. T1 read A, and T1 write A. Whenever T1 write A, I introduce another version of A. And then T2 begin. T2 try to read A. Which version of T2? Which version of A should T2 read? A0 or A1? Who think T2 should read A0? Who think T2 should read A1? In this case, T2 read A0. Why? Because T1 happens in its own sandbox. When T2 start, it starts from a state of the database that T1 hasn't committed yet. So all the changes in T1 hadn't been reflected into the database. So T2 should read A0 because that happens before T1 commit. Because T2 started like before T1 commit. And then T2 write A. What would happen? It's going to create a new version of A, right? So here, like 300, something like this, and update the timestamp. Can T2 commit? In this case, when T2 tries to commit, two things could happen. The first thing is you could allow T2 to commit. The consequence of that is when T1 tries to commit, you know you are going to roll back T1 because there will be a conflict. The alternative thing is whenever T2 wants to commit, you roll back T2. Because you know if you allow T1 to commit, if you allow T2 to commit, T1 going to waste a whole bunch of computation, and then at the end of the day, you know you have to abort T1, assuming T2 committed. Another thing you could do is you say, yeah, when I want to commit T2, I cannot do that because if I committed, some other transaction is going to be aborted. So you can roll back T2. Make sense? In this case, assume you abort T2, T1 can proceed. T1 doesn't know T2 being aborted. That's the beauty of this. Every single transaction happens in their own sandbox. Okay? And then essentially T1 could commit. Now let's look at one example. Okay? So then we have PostgreSQL here. Yeah. Now we have MySQL. Okay. Now we have this two PostgreSQL window here. And then what I'm going to do is to first set isolation level. Here I'm going to set that to repeatable read, which is going to be very clear why I said this in 5 minutes. It's going to be very clear to you guys why this happened. Okay? So I set both sessions. Maybe. Okay, so I set the isolation level of both sessions to repeatable read. And then one thing I can do is I can select my current transaction ID. Okay? There's one function in PostgreSQL allow you to do this. So once you run this on T1, T1 is the one on the left. You say, yeah, so this ID, okay? T1 has the ID timestamp 753, T2 754, okay? That's the timestamp of the current transaction. And then I have relation R. If I, for example, select, so each of these relations in PostgreSQL has two hidden attributes, xmin and xmax. That is the interval, okay? For example, do this from R, then you'll see a relation look like this. The A and B, the third and fourth column, are the real content. I have two tuples here, 0, 0, 1, 1. And then you can see the timestamp, xmin and xmax. Okay? So in this case. And then if you do the same thing, so we do another thing. If you say in T2, I update this R. Will this one get stuck? Well, this transaction, I read something. Now, this transaction try to update the same relation. From our previous demo, if this is my SQL doing logs, this one will get stuck. Because, yeah, there's no way I can update it because someone already read this. T1 is holding the shared log on that thing, right? Who thinks this one will get stuck? You get stuck? No? Who thinks this one will not get stuck? Okay, you guys are very hard to trick. Okay, if you do this, you're going to update it because try to update the local snapshot. And then what if in T1 I read again? Am I going to see the updates from T2? No, because T2 only reflects the local snapshot. If you read again in T1, you are going to see the same tuple. But the only difference is you'll see now the xmax of the second tuple being updated by T2 changed. That is the interval. Okay, make sense? Every single transaction that happens after this should see it, right? So this is the timestamp, but not T1. Make sense? Any questions about snapshot isolation? Okay. So as you can see, right, if you are really being correct to be optimistic, if your workload is something you can be optimistic about, this thing could be extremely efficient because they do not wait for each other. So let's look at another example, right? So in this case, you have T1 read A, T2 read write A, T1 write A, T2 commit before, and T1 commit. Do we allow T1 to commit? If you are doing snapshot isolation. No, right? You need to either abort one or the other. Okay? Because there's no way T1 can overwrite the updates of T2. Okay? What about this one? It's the same, right? There's no way T1 can update, can actually overwrite that. What about this one? It's the same. Okay? So these are the cases when you go back home, look at them carefully, and try to think about why you cannot allow T1 to commit. The hello idea is both T1 and T2 coming from the same state. Okay? When they start, they will copy the same state, and then T1 simply cannot overwrite it. Okay? So this case is fine. Okay? If T2 commit, then T1 begin, right? And T1 commit is going to be fine. Okay? The whole bunch of interesting cases that you can look at and go back home. But one thing that's interesting is I want to look at kind of limitation of snapshot isolation. It has a whole bunch of good properties. Okay? So there's no read or write transaction is being blocked because they just proceed. blocking only happens when some transaction try to commit. The overhead, right, you need to keep the right side of transaction only, right, which could be very efficient, and sometimes you have to keep out version anyway inside your database system because you want to go back to the past. There's no deadlocks because there are no locks. There's no, but sometimes you need to roll back something when it's not necessary. But there's a very big problem for snapshot isolation. That is, it actually doesn't enforce serializability. Now let's look at one example about why. So assuming you have this case, you have a system where you have, for example, 2 doctors in the hospital, A and B. And your integrity constraint would be, I need to have at least 1 doctor on duty. I cannot set both free. Okay, that's my integrity constraint. Transaction T1 try to set A to be free. Transaction T2 want to set B to be free. In the beginning, both doctors A and B are not free, so my integrity constraint is being respected. If you do the snapshot isolation and look at this schedule, will that be okay? It's okay, right? Because within each T1, it's fine. I set A to be free. I commit. T2, when T2 started, the snapshot of T2 is a case where both doctors are not are on duty. Then T2 release B, commit. T1 started before T2, and T1 committed before T2. If you do snapshot snapshot isolation, this is fine. But what's the problem? The problem happened at the end. In the end, we'll merge both back. Both doctors are free. You start to violate your integrity constraint. This is a counterexample about why snapshot isolation doesn't give you serializability. Because here you have 2 transactions. Each one of them is consistent. For any serial schedule, you will have something consistent in the end. But snapshot isolation is going to allow this schedule that's actually not consistent in the end. So what actually happens is when you update 2 different objects, and when you, like in different transactions, when your integrity constraint is being enforced over all those objects, you can only check integrity constraint for every single snapshot. And when you actually merge them back, it's very similar when you use GitHub to actually merge code, right? So sometimes this type of thing will happen because someone is changing this piece of code, someone is changing this piece of code. They are okay when you run them individually, but when you merge them back, it could have a problem. So this is one such case that is naive snapshot isolation will actually not give you serializability. So here's another example that when you go back home, you can actually look at, right? So this is actually another counterexample. So what can we do? In PostgreSQL, what they are trying to do is something called serializable snapshot isolation. By default, that is what you have. If you set the isolation level to repeatable read, you are going to recover what we talk about in this course. That is the thing that doesn't give you serializability. Okay, so that's why we need to set that in the demo. Okay, that's all about isolation. Okay, so on Friday we are going to talk about how to recover from failure, atomicity, and also durability. Okay, so before we go, there is the teaching evaluation. So please give us feedback. Okay, so give us feedback. Some of them we cannot fully integrate this semester because we are almost done, right? But I promise you, right, so it's going to be there next year, okay? Please just put in your feedback and that's it. I'll see you guys on Friday. Yeah.